Right. Okay. So everybody, we're starting on the section of stoichiometry today, and stoichiometry deals with moles, mole ratios. We're going right back to the very, very beginning for this section. So I'm going to start on my whiteboard before I go on to other things, and I'm going to explain to you how I see moles and how I see moles fitting in with everything else. Okay. So the first thing is I like to draw a picture with moles. Now, I know that most of your teachers will put moles with an E on it, so M-O-L-E-S. It's a bit of an irony because we say it's moles with an E, that's the official thing, and then we say, oh, but we're going to abbreviate it and take the E out. So I have a rule, I never put an E in, and it's never going to cause an issue if you don't either. There are 4 equations that we can use to work out the number of moles. Now, for many of you, one of the first problems that people have with moles is that it's a foreign concept. You don't necessarily understand what it is that you're looking for. So I'm going to start by defining moles in terms of the number of particles, which is in fact where it comes from. And the first equation that we deal with when it comes to moles is that the number of moles is equal to the number of particles divided by Avogadro's constant. Na is Avogadro's constant, and it is equal to the value of 6,02 times 10 to the 23. And basically that gives us our definition of a mole. A mole is 6,02 times 10 to the 23 atoms, ions, molecules, or particles. I personally like the use of the word particles because particles can never be wrong. If I'm talking about atoms and I suddenly start talking about atoms of water, it's wrong because water is H2O. It consists of 2 or more atoms bonded together, and therefore we really should be saying molecules of water. So some people get their knickers in a twist because you say atoms of water. Also, you can't talk about molecules of neon because neon is just Ne, it's a noble gas, and it's only ever going to be an atom. Whereas if you use the word particles, it covers whatever you're talking about. Particles is a little bit like thingamabobs, thingamajigs, okay? It covers whatever you're talking about. So I can talk about a mole of neon particles or a mole of water particles, and then the word particles just kind of adjusts to whatever it is that I'm talking about. So over here, if we ever want to know how many moles of something we have, we're simply going to say that our number of moles is equal to our number of particles, capital N is particles, divided by Avogadro's constant, which is this number. Now, please note, this is while the definition of, while it provides the definition of a mole, it's also the least likely thing that you're ever going to get tested on because we can't physically count out how many particles there are. So when it comes to matric, this section, it might come up if they talk about how many electrons are moved, and you can work up the mass of the electrons and then the number of moles of electrons, and then you can work through in a weird kind of way there. But usually particles are not examined at all. Okay, so that's the first formula and the first arrangement we're going to use. The next one, which most of you are quite experienced at, is looking at the link to mass. This, please note that whatever we're looking at is a pure substance. And the reason it assumes it's a pure substance is that I cannot take the mass of salt water and then put in the molar mass of either salt, sodium chloride, or water, because it's neither of those. It's a mixture, and depending on what ratio of salt to water you've got, you're going to have a different molar mass. So our mass has to depend on something being a pure substance. And over here, the equation that we're going to use is that the number of moles is the sample mass over our molar mass. If you look very carefully, maybe you'll see it, the sample mass here is a lowercase m and the molar mass is an uppercase. So this here is my sample mass, which is measured in grams, and this is my molar mass. Actually, let's just write that out. Molar mass, which is measured in grams per mole. Just something important here. this capital M has many different names. Some people call it formula mass. Some people call it molecular mass. It's an atomic mass if we're dealing with something like neon that's atomic. I prefer to just use the word molar because then it's the mass of 1 mole. And because it's the mass of 1 mole, it doesn't matter whether it's a molecule or a formula or what it is that we're looking at in particular. All right, so that'll allow you to kind of work around whatever it is that you're dealing with. So this mass is most commonly asked for solids, just so you know. Okay, so this is solids. Sometimes I guess gases, but it's got to be pure, whatever it is. Okay, the next equation that we're going to link to when it comes to moles is going to be volume of a gas. Now you'll notice I emphasized it has to be of a gas because a lot of people mess up big time here, and the second I give you a volume, you plug it into this formula and then it doesn't work. So here the formula is the number of moles is the volume divided by the molar volume. Now our molar volume, as you learned in grade 10, the molar volume at conditions of STP is 22,4 decimeters cubed per mole. Okay, or I could, if I wish, I could take away this per, in fact, let's make it per mole, and I could make it moles to the -1. It's kind of the opposite way around to what you're used to. You're used to having moles per decimeter cubed. This is now volume per mole. So this value of 22.4 is specific to STP, standard temperature and pressure. The standard temperature is 0 degrees Celsius. So we've got to take that gas and put it on ice to get this volume. The standard pressure is 101,3 kilopascals, which is also the equivalent of 1 atmosphere, which is the pressure that you and I are under right now. So right now, you've got that atmospheric pressure down on you if you're at sea level. If you're at a higher altitude, it'll be slightly less. Okay, but I'm at sea level, so right now I've got 1 atmosphere. So if I were to get a balloon, blow it up with nitrogen, stick it in a container filled with ice, that is the volume that I'd get for each mole. So if I have 1 mole of any gas, very important here, any gas. In fact, it's even to the point where the identity of the gas doesn't affect the answer. Because we're assuming here that we're dealing with ideal gases. Okay, ideal gases, just for the record, was a section that you should have touched in grade 11. You should have covered an equation PV is equal to nRT. But please note, this is not the focus at all in matric, but it is one of the ways that they get the volume. In a matric exam, they are allowed to change it to give you a molar volume under other circumstances. So they may randomly in the question say, the molar volume is 25 decimeters cubed per mole, and then you go, fantastic, it's 25, and you plug in 25 instead of 22.4. So if they give you an alternative value, please use it. All right, so back again, this over here, N on all of them, just for the record, is moles. Okay, so here we're going to have volume in decimeters cubed, and this value will be 22.4 decimeters cubed per mole. And the decimeters will cancel, sorry, the decimeters cubed cancels with the decimeters cubed. The per mole is on the bottom, so it comes to the top, and we get that moles equal moles. So our units cancel themselves out rather conveniently. Once again, this formula, gas. Not a gas, not this formula. So I need you to make a mental note that goes, is it a gas? Yes, it is. I may use that formula. Is it a gas? No, it isn't. Don't touch that formula. Okay, you will become a statistic. We will laugh at you. We'll be like, gosh, haha, this kid didn't know what they were doing. Okay, please don't be that kid. Make sure that you use the right formula and you don't fall into the common pitfalls. All right. So far we've done particles. Ooh, all of them have got boxes except for that one. Particles, mass, volume of a gas. And the last thing that we're going to look at here is the concentration formula. Now, concentration has to do with the ratio of solute to solvent. Solute dissolves in solvent to make a solution. Solute is the substance present in the smaller quantity, and solvent is present in the larger quantity. However, our formula usually assumes that the solute has been put in the solvent, and our calculation says concentration is number of moles of solute divided by the volume of total solution. Okay, so N is our number of moles, same as this N, and this N. B is our volume, which is in decimeters cubed. And C is the concentration. I see there's a question. I'll get there now. It's the concentration, which is in moles per decimeter cubed. All right. Just a second. Let me quickly check. Ma'am, can we use the volume ratio instead of the mole ratio in an equation to solve stoichiometric calculations? If it's volume to volume to volume, then you may. Otherwise, I'd recommend that you go through moles first. I personally have never been a fan of mass to mass or volume to volume. I tend to view it as I do this diagram, where everything that I ever work out goes through moles. So if I get the volume of a gas and I need to work out what the mass is, I use the volume, work out the moles. You go from moles directly to particles. All right. Is everybody good with this? I'm going to stop sharing for just a second. I'm going to quickly put you guys to thumbs up if everybody's good. Did everybody get that far? Okay, fantastic. First screen's good, second screen's good, third screen's good. Yay. All right. So, okay. Now, when it comes to layout in chemistry, I'm very fussy about how we lay things out. My background is actually in chemistry. And when you're a proper chemist working in the laboratory, you're not dealing with one substance at a time. You're dealing with hundreds of different things. Okay, please don't worry if you didn't get all the notes down. I'll send screenshots later, as well as the YouTube video will be available for you to go through and have a look if you missed anything. Right, I've just got quite a lot to get through. Okay, so continuing here. Quickly take a screenshot. There it is. Grab it quick. All right, I presume that's taken. So whenever I work out anything, I always remind myself what it was that I was looking at. All right, so if I'm looking for the number of moles of copper sulfate, I will remind myself that is the number of moles of copper sulfate. So I, in fact, put it in as part of my formula. Number of moles of copper sulfate is mass over molar mass. When I'm working out the molar mass of something, I remind myself that I'm working out the molar mass of copper sulfate. It just makes it so much easier. Also, if I get asked a question later and I need the molar mass of copper sulfate, I go and look at what I put there because I know it and I know where to look. If I haven't labeled it, I've got a whole bunch of molar masses and I don't know what they all stand for, and then I've got to redo the same work again. Also, it makes it very clear to the examiner what you're talking about. I am saying that the number of moles of copper sulfate will be equal to twice the number of moles of zinc. No confusion. They know exactly what I'm talking about. Or I could even say that the number of moles of copper sulfate is whatever that number is, 2. And then the number of moles of zinc is 2 times 2, which is 4. And suddenly everybody knows, and please always units, but I'm just quickly demonstrating here. Make it clear in your layout what it is that you're referring to and how it is affecting whatever next it is that you're looking at. All right. Now, before we go on to moles and mole calculations, I have to take one further step back. And I know a number of you are not going to like me for this, but we've got to. When it comes to writing down formulae, quite often in a question, they're going to tell you zinc nitrate. And if you don't know what zinc nitrate's formula is, you and ah and get it wrong, and then it doesn't matter what you do any further because your molar mass is wrong, the number of moles is wrong, and you may as well not written the exam. Okay, that's a bit of an exaggeration, but you get the idea. So we've got to make sure, okay, there's no S, we've got to make sure that you know how to put together your formulae. So you all hopefully know that zinc is typically Zn2+, and that nitrate is NO3-, and that when we put them together, we swap their oxidation numbers. We always write the thing that's positive first. So this is going to be Zn. This number goes here. This number goes here. So that is going to make it Zn, then the 1. This is 1 minus 1. I'm only going to write the 1. I'm going to write it here so smally, little, not there at all. I'm going to delete it just now. And then over here, we've got nitrate, which is NO3. The 2 is going to come from there and get brought down to there. But at the moment, it looks like it says NO32, which is rubbish. It's saying that there are 2 nitrates, so I must put brackets around it. We never include the number 1, so I'm going to take that off. All right, so it's very important that you know how to put together your ions and your polyatomic ions to get the correct formula. Because if your zinc nitrate looks like this, your formula is going to be wrong, and everything you ever do with it will also be wrong. So what I'm going to quickly just spend a few minutes, not very long at all, on is I want to tell you where we get these numbers from so that you can make sure that you know where all of them are. Okay, so first things first, I'm going to quickly just share that with you. There we go. Okay, so this over here is my periodic table. And on it, you hopefully know we have the elements arranged. Anything in group 1 typically will have a number of +1. So if I have lithium, it's likely to be Li+. Anything in group 2 will be +2. Anything in group 3 will be +3. And please, when I'm talking about 3, I mean Roman numerals. Anything in group 4 will be plus or minus 4, but it's also not likely to form an ion, so you usually can ignore this group completely. Anything in group 5 will be -3. Anything in group 6, -2. Group 7, or the halogens, -1. And group 8, your noble gases, doesn't form compounds. So, quick example while we're here before we move on. If I asked you what is the formula of sodium oxide? Sodium is Na+, oxide is O2-. Then I follow my rules. The positive one gets written down first. The negative one gets written down second. I also then take this plus and it goes to the end. So it's going to put a 1 there because this was +1. And this -2 puts a 2 there. We don't put the sign, just the number. So because of this, that gets a 2 and this gets a 1, but we don't bother writing the 1. So sodium oxide is Na2O. Can I please, just before I move on, ask everybody to quickly, I'll give you a second to check you've got this idea, ask everyone to write down the formula for me for aluminium bromide. Okay? Quickly try and find the 2 elements. Remember that anything that ends with the letters IDE comes from usually the negative ions over here. Okay. All right. Quick question, what happens to the elements in the middle? These typically tend to be +2, except for silver and mercury, which by default become +1. All right, so I'm going to give you just a second to quickly do that. Okay. All right. Okay, I'm going to presume that everybody had, if that was enough time, maybe had enough time to start going through that. I'm not going to give you a huge amount of time because I don't want to take too long on this particular aspect of the section. Let's quickly have a look. So if I look for aluminium, I find aluminium over there. And I look up and I see it's in group 3. So this is Al3+. Then I look for bromide because it's an ion, it ends in IDE. So bromine makes bromide. I see it's in group 7. So that's Br-. Then I remember that when I bring these down, that's going to bring a 3 there and a 1 there. And then I write down that it is AlBr3. Also be careful of your uppercase versus lowercase. I freak out when my students write NA, even more so when they write NA, because they're deliberately making it big and little. And I'm like, a little a doesn't make it lowercase. It's got to actually be lowercase. So similarly, CL freaks us teachers out. Please, it's got to be a curly L because it's lowercase. Na. As soon as that's an A, it's capital. And I cannot tell you how much delight we have in marking you wrong for those things. So please, if you look here, if it's a lowercase there, if it's a lowercase there, you'll see all of the second letters are lowercase. Please make yours lowercase as well. Don't give us good grounds for taking away your marks. Okay. Now, one last important thing on this, and I'm just going to quickly clear because I need a bit of space. I'm sure you all can remember +1, +2. You should have been doing this for a good couple of years already. But I want to remind you what happens if we've got magnesium oxide. Ma'am, what if you have 3 parts to your compound? Oh, okay. So if we have 3 parts, then we're dealing with a polyatomic ion, and I'm going to cover polyatomic ions in just a second. Okay. Everything that I've so far been dealing with is directly from the periodic table. So if I now asked you to do magnesium oxide, magnesium is Mg2+, because it's in group 2. And your oxygen is going to be 2- because it's in group 6. So if you look here, you'll see that if we were to bring them down, we should bring down a 2 and a 2. But the rule is that if both of them have the same oxidation numbers, they cancel out. So we simplify first. So the 2 cancels with the 2, leaving us with both of them as 1, and we just write MgO. If I did carbon 4 plus, and oxygen 2-, we do something even stranger, where that cancels with that, but they divide. So we're going to get a 2 there and a 1 there, so that gives us our CO2. And if we have sulfur 6+ and oxygen 2-, then we do an even weird thing where that becomes a 3, that becomes a 1, and we end up with SO3. Although usually these are not done in terms of oxidation numbers because they're both non-metals. So usually this applies to ionic compounds, which is a metal and a non-metal. But some people do still view in terms of oxidation numbers, which you'll touch on again when we do redox, is that you're dealing with those charges over there as well. And we can, in fact, think of the oxidation numbers here. And it kind of links to the same thing. All right. I'm going to clear this. And I'm going to quickly go back to sharing my whiteboard because I want to quickly write down the most common polyatomic ions. Now, please note there are many more polyatomic ions that I'm listing here. You can go and ask your teacher, your own teacher, for a list. I've got a lovely, big, long, crazy list. But the ones that I'm about to list here are the ones that I feel are likely to come up. Okay, so instead of you learning all, I guess there are about 50 of them, what you can do is you can focus in on specific things that you're likely to get asked. Okay, so you are likely to get asked nitrates. Nitrate is NO3-. Just for the record, the heading here is polyatomic ions. Nitrate, NO3-. Sulfate, please note it's technically spelled with an F. I still spell it with a PH, but you can spell it with an F and it's technically more right, more correct. SO4 2-. Carbonate is CO3 2-. Phosphate is PO4 3-. Hydroxide is OH-. Ammonium is NH4+. Ethanoate is CH3COO-. Okay, so I would say there are a lot more than those, but these are the ones that you're most likely to get asked in a test or in an exam. And please remember with your polyatomic ions, if there's more than one of them, you add in brackets. So if I told you that we had, actually sodium's a bad choice here, but we'll quickly do it. Sodium carbonate. Sodium is Na+, carbonate is CO3 2-. So when I swap them, it's the 1 and the 2- that we swap. So it's going to be Na2CO3. So that 1 went to here and I didn't write it, and that 2 went down to there. The one that I did mean to do that I kind of messed up on, but we'll do it now, is, wasn't that one either. Okay, just quickly give me a second. There we go. Aluminium sulfate. Okay, so here we'd have Al3 plus and SO4 2 minus. So we'd have our Al followed by a 2, and then there'd be SO4, and there are 3 of them, so we put the 3 there. Now, just something that a lot of you tend to do that I really worry about is please leave this 4 alone. This 3, leave it alone. This 4, leave it alone. This 3, this 4, this 4, this 3. Leave them alone. They're not part of the oxidation number. Don't suddenly bring this 4 into something about putting a 4 here, or you guys, you'd be amazed as the crazy things you guys do with these questions. Make sure that it's only the charges that you put up. All right, I'm just going to quickly get rid of all of that so that you can take a nice, neat picture of what you should be doing here. Okay, please make sure that you know at a bare minimum these. There are probably a lot that I've left off here, but I think that if you kind of got the gist of the ones that are going to come up, you've got a good chance that you'll manage to swing through the ones that they don't. They often are nice and they do give you the formulas in matric. They don't have to. Okay, and definitely in grade 11 they didn't. Okay, so the reason I've gone through this is that a lot of the questions that I've put forward going forward don't always tell you what the formula is, and if you don't know what the formula is, you're stuck before you even start. All right, so I'm just quickly going to stop sharing here, just check that everybody's okay, and then we'll move forward. Okay, any questions, anyone? Okay, so just for the record, the things where you've got 3 different elements, those must involve a polyatomic ion, otherwise it doesn't work. All right, is everybody good with this? Yes? Okay, fantastic, good. So what we're going to move on to now is I've kind of selected a bunch of questions that are very elementary. I do know they're elementary, but I feel that we've got to build up the skills for the people that are particularly weak. And depending on how far we get today, by the time we hit Wednesday's lesson, I'm going to drag out all the scary questions and really challenging questions. We might get there already today, but I'm not making any promises ahead of time. Okay, so I'm going to share my screen. And then I'm going to jump to this question. Okay, so now that I've discussed all the different 4 ways that we can work out the number of moles, I'm actually going to take a step back. We'll come to those just now. And I want to remind you of a couple of things that pop up every now and again, in every section. The most recent one that I saw, percentage composition and empirical formula on a matric paper, was organic chemistry. Everyone freaked out because they hadn't done them since grade 10. So I'm just going to quickly remind you how to do percentage composition. This one's mine, this one's yours, this one's if we need more practice. So the question says, determine the percentage composition of calcium hydroxide. When we talk about percentage composition, we want to know how much of the calcium hydroxide by mass is made from the elements in it, calcium, oxygen, and hydrogen. Now, the first thing we've got to do is get the right formula, or we're lost from the start. Calcium is Ca2+. Hydroxide is a polyatomic ion, and it's OH-. So my overall formula, these 2 swap, and I get CaOH2. Okay. Now, with this formula here, we're going to start off always, whenever we do a percentage composition, by working out the molecular or molar mass. The molar mass of calcium hydroxide, we're going to get by looking at, so that capital M is my molar mass. There's the formula of it. We're going to add together the molar masses of calcium, oxygen, and hydrogen. Now, I'm unfortunately not going to lose my screen here. It's going to cause a disaster. So I'm going to jump to my periodic table. I did send through a link to most of, on the group to most of you, for the periodic table so that you can have a look at it if you needed to. And I just quickly want to point out where you get this mass from. So calcium, it's that number over there. It's your atomic mass number. So calcium's 40, oxygen is 16, and hydrogen is 1. Okay, that is where we get all of the masses from. You will be given a periodic table in your matric exam. You do not need, and at any other exam, you do not need to memorize these. Okay, so you don't have to go and memorize them to make sure that they're still stuck somewhere in your head. All right, let me just erase those now because I was quickly trying to get them. There we go. So showing you those numbers that I looked up, calcium was 40. Oxygen was 16, and there are 2 of them. This is calcium hydroxide. So it effectively looks like that. So here I'm going to have 2 times 16 plus 2 hydrogens is 2 times 1. Okay, do we assume 100%? Yes. Okay, so whenever it's a compound, sorry, I'm not quite certain what the do we assume 100% meant, but this here is us working out what percentage by mass is there. All right, do you want to ask? There we go. Do you want to ask? Okay, you're welcome if you wish to just unmute yourself, ask a question, then mute again if you need to. So the molar mass of calcium hydroxide is 40 plus 2 times 16 plus 2, okay, which gives me an answer of 74 grams per mole. Now, we can sometimes get very particular. Some schools teach that if there's an R there, which means that it's relative, you don't put in units at all here. I find that I don't get too caught up in that. I know that you're not supposed to have the units, but if you just call it M, then you're allowed the units. So that means that 1 mole of calcium hydroxide has a mass of 74 grams. Okay, it's 74 grams per 1 mole. Now, if I look at this, I can see that there are 3 different elements here. There's calcium, there's oxygen, and there's hydrogen. I, in fact, had to use that to work out what all of the different parts were that contributed to the molar mass. So if I want to work out the percentage that is calcium, I can now go back and say, of the 74, that bit was calcium. So 40 grams out of the 74 grams from each mole times by 100, because I want to get a percentage, will give me the percentage that is calcium. So 40 divided by 74 times 100 gives me that 54.05% of calcium hydroxide is calcium hydroxide is calcium. Okay, so we don't even need to care about how much calcium hydroxide we have. If we've got 1 gram, 54.05% of it is calcium. If we've got 10 tons, still 54.05%, provided that we have 100% pure calcium hydroxide. But we're assuming here that when we ask you to do the percentage composition, it's not a trick question, and that would be the percentage composition of what we've actually got. The percentage of oxygen, well, oxygen, there were 2 oxygens, so it contributed 2 times 16, which is 32. So it's going to be 32 out of 74 times 100. So 32 out of 74 times 100 gets me an answer of 43.24%. And the last one that we have to do is the percentage that's hydrogen. So if I look here, hydrogen is 2 times 1. So it's 2 out of 74 times 100. Now there's always one bright kid who goes, couldn't you just take 100 and subtract these 2? Yeah, you could. However, my approach is that I use those for my check. What I check at the end is if all of these add up to 100, then I know I didn't make a mistake. And if they don't add up to 100, then I know that I've either rounded strangely or I have made a mistake. So over here, I get 2.70%. In fact, you already see that I may have potentially made a small mistake. As long as I get to 99.99, it usually means that the rounding came about where maybe this one had a 4, this one had a 4, and this one had a 2. So all of them got rounded down. It does occur on some cases, but usually the way you can remove that is if you then write them all to 3 or 4 or 5 decimal places. So if I do that, I get to 99.99, and I'm happy that that's close enough that it was probably just a small round. So this is how we work out percentage composition. Now I know it's very straightforward, okay, but we just got to make sure that we cover all bases. Could I write O2 instead of oxygen? Absolutely not. O2 is not the element, that's a molecule. So when it comes to these, you may not write O2 or H2. Everything must appear exactly as it would on the periodic table. So nothing should be diatomic, nothing, we can't even work out the percentage. Sometimes there's one little trick where we do this, and that's that sometimes you can work out the percentage that's water. But that comes in when we're dealing with water crystallization, which I'm going to cover later. But nothing else gets done like that. It's just a dangerous approach. Okay, ladies and gentlemen, I know some of you haven't done these like this with me before, but now what I'd like to do is I'm going to give you an opportunity to do question 2. Before I throw you in the deep end, I'm going to help you to work out what the formula is of lithium nitrate, because if we don't do that, we may have a total disaster. Okay, so I'd like all of you right now to try and work out what you think lithium nitrate should have a formula of. Okay, I'm going to give you just a few seconds to write it down, and then I'm going to give you the correct answer. Okay, so I've got lithium is Li plus because it's in group 1, and nitrate is NO3 minus because I've memorized it off by heart, which means that my formula is LiNO3. I hope that you all got that correct. What you're then going to do is you're going to work out the molar mass of lithium nitrate, and then after that, I'd like you to work out the percentage of lithium, the percentage of nitrogen, and the percentage of oxygen. Okay, what I do here is I pause sharing my screen, which means I can carry on working while you're working. All right. I'm going to give you a little bit of time to do this, but I'm going to stop sharing my screen while I also work out the answer. Okay, please get working on it now so that you can check that you can actually do it based on what you saw me do in the previous one. Okay, I think everyone should have a periodic table. I think there's only one group that didn't get, so I'll quickly send that out to you now. Okay, is everybody there? Is everybody getting there? Cool. Please shout if you're really struggling.
Ma'am,
Yes.
what happens if we say it's an impure compound of lithium nitrate?
Okay, we're not yet assuming that. Then you'd be working out something called percentage purity instead. So our assumption at the moment is that everything is pure and we're only working out percentage of whatever's there that is pure. And this is important because sometimes whatever's in there could tell you, I don't know, something else about what's going to happen, how many particles, how much of something you have. So we will be looking at percentage purity, which I guess is kind of similar, but a little bit later. This is now, right now, just the exercise of working out percentage composition. Okay. Okay, just quickly answering a question. Somebody said, what does the relative mean? Relative is actually because everything when it comes to stoichiometry, the number of moles we have, or the molar mass of something, is relative to the mass of carbon 12. So it just means that everything on the periodic table is standardized against the mass of 12 grams of carbon 12. So it takes away the units from a question, okay, because if it's relative to 12 grams of carbon 12, 12 grams of carbon 12 contains a mass already. So it doesn't usually, well, it isn't usually one of those things that we focus on. It isn't usually something that you need to worry about too much. Okay. Can I ask, as soon as you're done with that, that you give me, and start opening this so I can see who's done. Thumbs up if you're done. Okay, good couple of you, good. Good, okay. Good, I'm gonna give you just a tiny bit longer because some of you may be a tiny bit behind everyone else, and I don't want to take this away from you just because I'm in a hurry. Okay, we've got enough across the 2 days, because I knew that this was going to be a section where some of you are exceptionally strong on, but I assume that with these lessons, you guys are actually making decisions as to whether you need to do a specific section or not. Obviously, I'd encourage you to do all of them, but I guess if you later discover you need to, you know that there's a bank of YouTube videos that you can go back to and catch up on later. But I personally think that live things makes more sense. So you get to ask questions, but yeah. Okay, I'm going to go through this. So I'm going to resume my sharing. Please note with mine, my numbers don't add up perfectly. So I suspect that this 5 I should have taken down. So I'm going to resume share. With all of mine, I went to 3 decimal places because I was worried it wouldn't work with less. But I, in fact, could have worked with less and it wouldn't have been an issue. So I got 10,145, 20,290, 69,570, and they were all close enough. I technically got 100,05%, but you get the idea as to how to work out the percentage of all of the elements. Now, usually in an exam, they're not going to ask you all of them because this, and this aren't testing you on different skills. So usually the question would be similar to the one right at the bottom here, which is to calculate the percentage of oxygen in aluminium oxide, which means we're only looking for one element out of all of them. So then what you'd need to do is work out the molar mass and work out the mass of one specific element out of the total. Okay, so this is just reminding you how to do percentage composition. I'm now going to move down. I'm going to quickly clear this. So anyone who needs to take a photo, please quickly do it. Okay, I'm going to clear this. And then we're going to move down to the next section. The next section that I wanted to go through here is empirical formula. But before we go through empirical formula, we've now been working for 45 minutes, which I think is a long time. And I know that most of your brains kind of shut off after 45 minutes. So whenever we do an hour and a half, I encourage you now, please quickly stand up, get a bit of movement, okay? Move around so that you don't fall asleep on me. Come, stand up properly. I'm going to do it too. Okay, stretch. Make sure that your body's still awake. Okay, because otherwise we end up losing you, which is a problem, especially when we're doing such a long session. Okay, so before I go any further, everybody happy, everybody understanding, everybody know where they are? Okay, can I quickly ask, just that I can check where I'm pacing this, who has managed, guys can't start with the questions yet, thumbs down. Okay, who has found that even though we've gone right back to the beginning, they've already learned something new? Is there anyone who's learned something new or been reminded of something? Okay, all right. You know what? It's a few of you, but it's enough that it makes sense. Okay, so my assumption always is we will get to the hard stuff, but we've got to start from the beginning or I am going to lose a large number of you en route. Okay, so the next thing that we're going to be doing, okay, just quickly checking. All right, yay. Thank you for saying totally helpful. Okay, so the next thing that we're going to be doing, ladies and gentlemen, is we're going to be moving on to empirical formula. Now, empirical formula is the simplest, that's probably spelled wrong, but anyway, it's the simplest ratio of the elements in a substance. So one of the examples that I pick on, that I know all teachers pick on, is hydrogen peroxide, H2O2. And if we look for the empirical formula of hydrogen peroxide, it actually just becomes HO. Because there are 2 hydrogens to 2 oxygens, so it's 1 to 1. Same thing if I were looking at maybe methane, C6H6. Suddenly the empirical formula just becomes CH. Every carbon has a hydrogen. Now, the reason that we look at empirical formula is one of the reasons that we're able to tell you what the formula is of a substance is that we've often sent it through a mass spec. And a mass spec has effectively, it's a tunnel, and you take the sample and you put it in, and it turns it into a gas, and then it charges it, and then the charged particles fly across the tunnel, and depending on the ratio of mass to charge, they take different amounts of time. You do not need to worry about how the mass spec works. But what will happen is, depending on how long it takes, we'll end up with little peaks telling us what masses we've got. So here, you'd know that carbon is 12, and oxygen is 16, and hydrogen is 1. And we'd get peaks where, imagine these were all units, the percentage of the total of all their heights would add up to 100, and we'd see here that there's very little carbon, and then there's quite a lot of oxygen, and quite a lot of carbon and slightly less oxygen. Depending on the heights of these columns and where their values are, we'd be able to work out what these different percentages are. But we don't now know what the formula is. We just know how many carbons to hydrogens to oxygens are. Okay, sorry, can I please ask anyone who's chatting on the general group, unless you want me to ask you to leave, please stop it. All right, I'm getting quite a lot of comments, and unfortunately they're distracting me. All right, thank you. So these different heights tell us about our percentages of carbon, hydrogen, and oxygen. Now, we don't know whether that hydrogen value that we get there is for 1 hydrogen or for 15. All that we can tell is the ratio of these to each other. So that's why we start with empirical formula. We can tell that for every 1 carbon, there's 1 hydrogen, but we don't now know if it's CH or if it's C2H2 or if it's C3H3 or if it's C4H4. We don't really know what the formula is, and that's where the empirical formula comes in. It gives us the ratio that we've got. Later, when we get the formula mass, that helps us to decide, oh wait, it's actually C6H6. We're 100% certain it's that one. So this process here is almost the exact opposite of doing percentage composition. It's now saying, here's your percentage composition, what's the formula? Okay, but bear in mind that the formula you're getting is simply the simplest whole number ratio. It doesn't actually tell you how many multiples of that you've got. So the steps that I find here that I do is I write out all of the elements. Now, just an important thing that many of you should know, but you don't always know, C, O, and H always get written C, then H, then O. That's the order that we write them in. Okay, so over here, I know that I've got 48.6% carbon. I know I've got 43.2, wrong way around. That's not hydrogen. I've got 8.1% hydrogen, and I've got 43.2% oxygen. The first assumption I make, and you have to write this down, is I assume I have 100 grams. You could assume any mass you want, but 100 grams is smart because that means that each percent becomes a gram. So this would become 48.6 grams out of 100, and 8.1 grams out of 100, and 43.2 grams out of 100. The next step that we're going to want to do is we're going to want to calculate the number of moles. Okay. Okay, quick question. Will you get them wrong if you write them in another order? No, but it may make it harder for you to identify these, because if we're giving you something that's got carbon, hydrogen, and oxygen, we're probably expecting you to figure out from here what organic molecule it is. And because we're trying to ask or get you to figure out what organic molecule it is, it helps if you've got them in this order. So it's just one of those like polishing things. Makes it neater, makes it more what we'd expect. So to calculate our number of moles, we're going to use the formula that the number of moles is the sample mass over the molar mass. Now, ladies and gentlemen, I know molar masses because I've been doing this for a really long time. If you need to look these up on a periodic table, don't feel stupid, do. The number of moles of carbon is going to be 48,6 divided by 12, because the molar mass of carbon is 12. This formula must appear somewhere. There is a formula mark for it, but I don't like to include it here because it gets very messy, okay? The number of moles of hydrogen is going to be 8,1 divided by 1, and the number of moles of oxygen is going to be 43.2 divided by 16. So 48.6 divided by 12, that gives me an answer of 4,05 moles. 8.1 divided by 8 gives me 8.1, and 43.2 divided by 16 gives me, did I do that right? Yes, I did. I got 2.7. Okay, so what we do now is we've got our first ratio of carbon to hydrogen to oxygen. We know that it's 4,05 to 8,1 to 2,7. Please just let me know if I've done anything wrong here, because I'm suddenly doubting the numbers, but I sometimes do that unnecessarily. They do all add up to close to 100, and there is definitely 43.2 divided by 16. Okay, now the first thing that we always do when we want a simpler ratio is we divide everything by the smallest number. So I'm going to divide everything here by 2.7. So 4.05 divided by 2.7 gets me an answer of 1,5. 8.1 divided by 2.7 gets me an answer of 3. And 2.7 divided by 2.7 gets me an answer of 1. Now, I have a rule here. Everything on an empirical formula has to have a whole number. If you end up with something that ends up with a 0.5, you times it by 2. If it ends with a 0.33, you times it by 3. If it ends up with a 0.25, you times it by 4. If it ends up with a 0.2, you times it by 5. If you end up with a 0.167, you times it by 6. Okay? If you end up with it gets messy after that, 125, you maybe times it by 8. But I find that almost anywhere below here, I start to worry that I may be doing the wrong thing and I just did bad maths. Okay? So these ones are the ones where I say go for it. Other than that, be careful. So here I'm going to times everything by 2, which means that my number here is going to be a ratio of 3 to 6 to 2, which means my formula becomes C3H6O2. And I'm sure that most of you who've already done organic chemistry can go, all right, cool. So I've got 3 carbons. I'm allowed an oxygen and another oxygen. And I've got 1, 2, 3, 4, 5, 6 hydrogens. Yay. Okay. So this could be propanoic acid. Doesn't have to be, could be propanoic acid. Okay. Since this is a carboxylic acid, it could also be any ester. And we're not 100% certain what it is, but it could be. All right. So I find that what I personally do as soon as I get to an answer is I try and link it to all of the molecules I've ever seen, which is quite a lot, and give it an identity. And if I can't come up with an identity, I do sometimes worry that that means I'm wrong. But usually if you can come up with an identity for it, you're prepared to cement it as your answer and go, yay, that's it. Okay. Now they tell us that the formula mass of the substance is 148 grams per mole. We weren't sure that this was this formula. It may have been C6, twice as much, H12, O4. Could have been. Don't know. Okay, so we're going to use the formula mass to determine whether we're right there. Okay, quickly, multiplications. So I'm assuming you're talking about this. Okay, sometimes once you've got to your first simplified ratio, and you've divided all of them by the smallest number. Remember here we divided everything by 2.7, so we could get one of them to a ratio of 1. Sometimes when you do that, you don't get to a ratio of whole numbers. If your ratio ends up with a 0.5, it means that timesing everything by 2 will get rid of this 0.5, and round it up to a whole number. If you end up with a 0.33 and you times it by 3, it rounds it up to a whole number. If you have 0.25 and you times it by 4, it rounds it up to a whole number. So if this answer, for example, had been 2,25, I would have times every single one of these by 4, because it then would have allowed me to get a ratio of carbon to hydrogen to oxygen, carbon, hydrogen, and oxygen that could give me a nice molecule. Okay, you don't always have to do this rounding, but you've got to be able or prepared to do it if they give you weird ones. Sometimes you're lucky and it just gives you a ratio that's nice and neat. Sometimes you're unlucky. Okay. Then it says, if the molecular formula mass is 148 grams, determine the molecular formula. So the first thing I'm going to do is I'm going to work out the molecular mass of what I've got. So molecular mass of C3H6O2, because I'm going to regard this as being 1 unit. Now, I don't know how many multiples of the unit I've got, but it must be a whole number ratio of what I've got. So I start by saying, all right, there's my empirical formula. What would the mass be if it was just 1? So there are 3 carbons, so it's 3 times 12. Carbon's 12, look it up on the table. Here we got 6 hydrogens, so it's 6 times 1. And then there are 2 oxygens, so it's 2 times 16. And if it's 3 times 12 plus 6 plus 32, we get that the mass here is 74 grams per mole. Did I do that right? 3 times 12 plus 6 plus 32. I did. So if I now want to know how many multiples of that I've got, I'm now going to go and say, well, n, which is the number of multiples, is 148 divided by 74. And I'm going to hope that this works. Good. It does. It gives me 2, which tells me that I don't just have one of these. I actually do have twice as much. So therefore, this wasn't what we had. We do, in fact, have more. So therefore, our formula mass is going to be twice as much. So instead of being C3, it becomes C6. Instead of being H6, it becomes H12. And instead of becoming O2, it becomes O4. So you can always go and check. If they'd said that the relative formula mass is 74, then I'd have said, cool, fantastic, that's it. But since it's a whole multiple twice as much, that tells me that I've got 2 packages. Just like we said here, this is 6 times as much. We may get this, but whatever the mass we have will be 6 times the mass of just the C and the H. All right. Okay, do you get the marks? No. So in this case, usually with working out molar masses and things, you'd get a mark just for getting to the end. Nobody really fusses about your values, but here you would have to show full substitution. So if you are fast enough and smart enough to work this out in your head, I can tell you right now, calcium carbonate has a mass of 100 grams per mole. Easy, stuck in my head, I'll never need to look it up. So if you know your formula masses, or you work them out quickly, or you put them on your calculator, as long as you're confident that you've got it right, you don't have to always show the working out, unless it looks like that's what the question's giving you the marks for. So if it really looks like that's what you should do, then make sure you do. But usually we assume that if you worked that correct, you'd get the mark. Okay, so if you got the correct answer, you must have had the correct method. All right. Ladies and gentlemen, I'm going to give you a second just quickly to take a photo of this. Okay. And then because I don't want to spend the whole of this week, well, this lesson and next lesson on it, I'm going to give you a question to do for homework. Okay. I know it sounds a bit crazy, homework, but I'm going to give you a question and I'm going to suggest that when you're done with it, you take a snapshot and you send it to me and I'll tell you if it's right. Okay. So I'm hoping that that'll make sense for anybody who needs to practice more, that they then know that they'd be able to try it, and I'll work out the solution later and you can send it in and I'll happily check whether yours is right. Okay, so here's your question. Determine the true formula of nicotine. True formula means its actual molecular, actual formula mass, not formula mass, actual, formula. If the molecular mass is 162.2 grams per mole, you may find that you just want to work on 162. Usually the Department of Education does not give you formulas that have decimals in them. You can leave it in for now, it'll just cause a bit of rounding. And the percentage composition is as follows over there. All right, So nitrogen's 14, carbon's 12, and hydrogen's 1. Can I please ask you just quickly to take a screenshot of that question so that you can do it and then come back to it later? So I want to make sure that we do some of the easy questions in between and then hopefully move through to the point where we're actually doing mole ratios already tonight. Okay, anyone object? Anyone really want us to check it? Okay, good. All right, I'm assuming that silence favors what I'm asking. Okay, moving onwards. The rest of these are really, really straightforward, at least for the first bit. So we should find that as soon as we do them, they're very quick. Okay, I'm going to be focusing on making sure that you get into good layouts. If your teacher's not fussed about layout, be careful, your examiner might be. So just make sure that when you lay it out, you do it as neatly as possible and as easily to follow as easy to follow as possible. So the first question says, how many moles in 4 grams of zinc? So I know I'm working out number of moles. I'm not 100% certain what the molar mass of zinc is. So I'm going to quickly jump. I'm pretty sure it's 65, but it could be 63. So I look over there and it's 65. I'm right. Yay. So I'm going to go in here. I'm going to start by saying that the molar mass of zinc is 65 grams per mole. Then my number of moles of zinc is going to be my sample mass over my molar mass. So it's going to be 4 grams divided by 65. Please, if they give you things and they don't have decimal places or the decimal places to 0, 0, you can cheat and just drop them. So 4 divided by 65 gives me an answer that I have 0.0615 moles. Now, one of the things you'll notice is when it comes to moles, I recommend putting in 4 decimal places for everything. I don't leave it to luck or to rounding up quickly. I want 4 decimal places because what's it, 0.06 moles, if you round it out to 0.6, that 0.0015 moles could kill you. And not if it's of zinc necessarily, but it's enough when it comes to chemistry that it could. Can I please ask everybody very quickly to just do question 2? So it's almost identical in terms of questions. I just want to check that everybody can. So I'm going to give you very, very quick because I know I took about, I don't know, half a minute to do that. I'm going to pause and do it at the same time while you're doing, and then I'll show you my answer in a second. Okay. Carbon dioxide is CO2. You should know that. Okay. Amara, have you got that? Has everybody got that? Okay. I know I'm not giving you a huge amount of time to do it, but it should. I don't want to have us where I'm taking a lot of time. I want to try and get through a lot of this so that we can spend all of the Wednesday session doing way more complicated applications of everything fitting together. So the answer over here, you should have got an answer of 0.1477 moles. If you rounded that to 0.15 moles, that's perfectly fine. So all of our answers are to a minimum of 2 decimal places. If you choose to take them that minimum of 2 decimal places, that's fine. Okay. Anybody who wasn't sure how we did that, please do speak up. But I think a lot of you have been doing this for a while, and this should just be touching on things to remind you again. Okay, if you need to take a picture, otherwise I'm going to clear it. In fact, either way, I'm going to clear it. Okay. Then the next section, so that was just a reminder here that because, sorry, I didn't actually go into that very well. Because we're doing moles and mass, we're going to say number of moles is sample mass over mass. That's specifically because they gave us the value in mass. All right, let's move on to the next type of question. How many moles in 50 million atoms of zinc? So here, as soon as we're talking about atoms or molecules, we're using the equation N is equal to N over 6,02 times 10 to the 23, Avogadro's constant. So here, how many moles? I'm going to say that the number of moles, and I could put in zinc, but to be honest, it doesn't matter here. This could be 50 million atoms of any element, and the answer would be the same. So here, this is going to be 50 million. You could write out the zeros if you really wanted to. It's not going to make a difference. And then divided by 6,02 times 10 to the 23. Please make sure in your calculators that you get used to working with scientific notation. I strongly suggest good use of brackets here to make sure that you don't divide things incorrectly and leave bits at the bottom or at the top when they should be at the bottom. Okay, and if I work that out, I get an answer of 8,3056. I'm going to call it 31 times 10 to the negative 17 moles. Okay, so that's me working how many moles there are. This next question is going to be working backwards. So you've been given the number of moles and you're looking for the number of molecules. Please note this N is for molecules, atoms, particles, whatever it is that we feel like we're looking for. All right, ladies and gentlemen, I'm going to quickly give you a chance to try and do that as well while I work it out independently, and then we'll compare in just a second. Okay. I should, by the way, have done the formula at the top. I forgot. Okay, I'm done. I hope most of you are getting near to being done. All right, I'm going to presume that everybody's nearly done. Anyone that wants me to wait for them for just a second? Okay, looked for a second like my resume share button was flashing there, so I'm going to take the hint. Okay, my answer over here, I personally like to always write out the formula. You've got to if you want the formula mark. And then we got the 1.34 is the number of particles divided by 6.02 times 10 to the 23. And that gave me that the number of particles was 8,07 times 10 to the 23 molecules. All right. Ladies and gentlemen, I'm hoping that you're managing to follow these. I think you should, being in matric. This is grade 10 work that we're carrying through. This is just to remind you again that whatever data you're given, you've got to plug that into the appropriate formula. All right. Once again, quickly take any snapshots that you need. I'm going to clear this, and then we're going to move on to the next type of formula. All right. The next question gets a little bit trickier, so I'll do the hard one. You can do the easier one. We're going to be working out the volume of gas. So we're effectively saying we've got a certain volume of gas, and remember this was the equation where you used N is equal to V over Vm. And our rule was that at STP, Vm is going to be 22,4 decimeters cubed. Sorry, that should be a positive, decimeters cubed per mole. All right. Now, the first question is kind of more realistic for the level that you're going to get. The ones we've been doing up till now, the kind you get when we're practicing the beginning of the sections. So it says calculate the volume of 20 grams of hydrogen gas. So our 20 grams of hydrogen gas, we first of all got to work out the number of moles. I suspect I may have given myself a little bit too little room here, so I'm going to work down the side to begin. So I'm going to say that the number of moles of hydrogen gas is equal to the sample mass over the molar mass. I had to do that because they gave me mass. That's what you do. So the mass that I got was 20 grams. Hydrogen gas, you need to remember, is diatomic. So it's H2. If you just do H and you work out 1, you're going to have a problem. So it's going to be 2 times 1, which is 2, which means that I have got a total of 10 moles. Then I move on to the formula, which says number of moles is volume over molar volume. The number of moles is 10. We're looking for the volume. Molar volume, we always assume that it's at, well, we shouldn't really, but I'm assuming here because I created the question that it's at STP. So I'm going to put in 22,4, and therefore I get that the volume of gas is 10 times by 22,4, which gives me an answer of 224 decimeters cubed. All right. Now, please note that this question, because it was linked to mass, did depend on us knowing that it was hydrogen. But a question where you just get to use this formula will be the same regardless of what you've got, because technically, if I know the number of moles, it doesn't matter what the substance is. Okay, so it's only when we're going from mass to moles and then to volume of gas that the identity of the gas matters. I'm going to ask everyone very quickly to please do question 2 while I pause sharing, and then I'll go over the answer in a second. Yes, sorry, there's a question that's come in. Do we always have to multiply it by 2 for all diatomic molecules? Well, you'd be working out the molar mass. So you need to remember that there are a bunch of gases that are diatomic. Nitrogen, hydrogen, chlorine, fluorine. Okay, you also need to remember that if I ever tell you bromine, it's also times 2. Okay, so those are the ones, oh, and oxygen. Those are the ones you've got to look out for as being diatomic gases. If you forget, oh, I'm not sharing it. In a second, when I share it, you'll see that I've just written down all of those names for you. All right. I presume everybody's nearly done, and I can carry on. Okay, there's a question here about definition of a mole. Do we say it's the same number of particles as 12 grams of carbon-12, or do we need to give Avogadro's number? It depends on how thorough you want to be. Technically, I think that both are accepted. So it's the same number of particles as there are in 12 grams of carbon-12, or it's 6,02 times 10 to the 23 atoms, ions, molecules, or particles. So either of those should be accepted as a definition of a mole. Moles have multiple definitions that are equivalent. If you really want to be fancy in an exam, you kind of just do a smash where you kind of say all of those in one go so that nobody can correct you and say, oh, but you didn't say something. All right, ladies and gentlemen, I'm presuming you've gotten through that. So here you just took the 50 divided by 22.4 and got that many moles. Please note, if this question changed and it wasn't carbon dioxide, but it was methane, or it was oxygen, or it was any other gas that I can imagine, it wouldn't change my answer because I still would have had 50 decimeters cubed. It still would have been at STP, and I still would have got the same answer. All right. Please, that's the list of all of the things that are diatomic, all of the elements that are diatomic that exist as gases. Please just make sure that you are aware of them and that you don't get caught out by them. All right, I'm going to quickly clear all drawings. Okay, and then the last thing that I wanted to cover on the very basics was the idea of concentration. So concentration is going to use the equation C is equal to N over V. Obviously, we can rearrange this. So N is equal to CV, etc. So the question that I'm going to be doing is the first one, and then I'm giving you guys the harder one just now. So what mass of sodium fluoride is required to make up, actually it's not that much harder, they're equivalent, make up 60 centimeters cubed of a 0,084 mole per decimeter cubed solution? All right. So the first thing I probably should do is write down what I know here. First of all, I know that I'm dealing with sodium fluoride, which means that the formula is NaF. Sodium is Na plus, fluoride is F minus, so it's NaF. The next thing that I know is the volume. Now remember, you do not work in centimeters cubed, and you need to know that 1,000 centimeters cubed is 1 decimeter cubed. Something that you may not know, a centimeter cubed is a milliliter, and a decimeter cubed is a liter, and there are 1,000 milliliters in 1 liter. Okay, so my volume here of 600 centimeters cubed becomes 0.6 decimeters cubed. And the question was, what mass? Now, there are equations that can link all of these together in one go. I'm not going to use them. I'm going to use 2 separate equations. I know some of you are going to tell me it takes longer, but I'm going to go this way. So the first thing that I look at here is I'm going to use this equation because I've got concentration and volume. And then I'm going to use the equation N is equal to little m over big M because I'm going to be working out the mass. So I'm going to start off by working out the number of moles of sodium fluoride. So I'm going to go back to this equation. Concentration is number of moles over volume. You can rearrange it, but I prefer to leave it with this in this order and substitute in. So 0.084 is equal to number of moles divided by 0.6. So my number of moles of sodium fluoride is going to be 0.084 times 0.6, which gives me an answer of 0.0504 moles. But the question that I asked, or that I needed to find here, was what is the mass? So I'm now going to go and work out the molar mass. I always imagine on my page that it's divided in 2 halves, and the right-hand side is where I work out my molar mass. The molar mass of sodium fluoride, I actually need to look up. So sodium is 23, wrong formula sheet, there we go. Sorry, sodium is 23 and fluorine is 19. So this is going to be 23 plus 19. Fluorine doesn't come up very often. So it's going to be 23 plus 19 gives me 42 grams per mole. So if we go back to work out the number of moles, we can say that the number of moles is the sample mass over the molar mass. I'm going to squeeze this in. So 0.0504 is equal to the sample mass divided by 42. So the mass, therefore, is going to be determined by multiplying those two together, which gives me an answer of 2,12 grams. All right, so there is another equation that you could use, which literally merges these two, and it says C is equal to M over MV. Basically, what it does is it replaces this N with those two, okay? But here you've got to remember that this is your molar mass, and that's your sample mass. And a lot of people tend to use this, but I don't know why. I never really used it when I was in school. I always did these two separately. So it's one of my habits that I don't do it. All right. Whew. We've got about 7 minutes left, which unfortunately means that there isn't going to be a huge amount of time for us to start linking in mole ratios and limiting in excess reagents and percentage purity, etc. But I felt that it was very important for us to go back, especially for anybody who in grade 11 wasn't paying good attention, or in grade 10 who wasn't paying good attention, which is why we've gone all the way back to allow everybody to build up a good foundation before we tackle the harder things. So I do apologize if there's anybody who hasn't learned anything new today. At least the one thing you'll know is that you know what you're doing. All right, so I'm going to quickly clear this. Okay, just quickly take a screenshot because I want to scroll down.
Because it's finished.
Okay, is there a question? Okay, please unmute yourself if there is a question. All right, so the question, yeah, Johan? Was there a question? Okay, if we use the formula, if you use C is equal to N over V, the formula that's got both of them, you'll never lose a mark. Okay, so both of them are permitted. What I'm going to ask everybody to do for the last question today, because it does involve linking two formulas together, and though it's not difficult, it's starting to head towards the right level, is I'm going to quickly stop sharing. I'm going to ask everyone to do this last question, and then we're going to quickly have a chit chat about what we're doing in the next session. All right. So can everybody please get started on that last one? Please don't leave yet. Make sure that you do the question first. Okay. Oh, and here's another check here. Can you work out what calcium nitrate's formula is? Okay, if you think you've got the answer, can I ask you to type it in on the chat? I'm using this as a cheat to check whether mine is right. Now I'm worried. Okay. Okay, I'm going to go back and try that again. Please, can I suggest I've so far had two different answers and they differ from mine. Okay, concentration was 0.12 moles per decimeter cubed. Oh, okay, I know what I did wrong. One mistake. Okay, Michael, I'll get to you in just a second. Okay, yes, Michael, what's your question? Okay, you got to give me a second because my molar mass was wrong. I forgot that there was the 2 afterwards, which I knew it was there, I just didn't use it. Okay, one of you has got the same answer as me. Yippee. Okay, and that someone was Faith. Okay, and I think it's a beta. Well done. Okay, I suspect that the place where most of you went wrong, I'm going to hope that this works it out for you to make it clearer. Let me quickly share. Okay, so if I share here, you can't see hopefully because my picture's in the way, is that your formula had to have calcium being 2+ and nitrate being NO3 minus. So when you cross multiplied them, you should have got Ca brackets NO3 close brackets 2. That is why I focused on that so much. So calcium's 40, there's only one of them. There are 2 nitrogens, each of which is 14, and there's 6 oxygens, each of which is 16, which gives us 164 grams per mole. Please, if you went wrong that early on, you've got a problem. Then my sample mass here is the 7.2. My concentration is the 0.12. And if I now move my picture out the way, the value that I got was 2,73 decimeters cubed. All right, so hopefully anyone who's got the wrong answer has picked up where they've gone wrong. I suspect, because I think most of you got most of the rest of the steps right, that it's probably here. That's why some of you should start with just going back and making sure you can get the correct formula to begin with. All right, please take a screenshot of that if you need to. All right, don't leave just yet. I want to quickly chat to everybody. Okay, so I'm going to clear that. And I'm going to stop sharing. Okay. All right, ladies and gentlemen, can I quickly ask, I know this was it was pitched at a low level, but can I ask who needed me to start from a level that low? Quickly give me a thumbs up if it was an appropriate level to just go back and remind you all where we started from. Okay, good. By the looks of things, I think a lot of you are understanding that when I go slowly, it's not because I think you all don't know anything, but it's that I'm worried that there may be little gaps that you've missed. And if we can fill those little gaps, then we create a way stronger foundation before we start piling all of our chemistry on it. Because if you can't do these, or if you're messing up on these, then when we're starting to do pH calculations where the concentration of something determines your entire pH, everything falls apart because you can't work out a concentration. All right, ladies and gentlemen, I'm going to continue with the rest of this and we're going to move on to the much harder stuff when I see you on Wednesday. Please note Wednesday is a full hour-and-a-half long lesson because I knew that stoichiometry was going to take us a little while, and if we were going to go right back to basics and build you up, we'd need all that time. So at the moment, well done, you've now got grade 10 stoichiometry back in your head. When I see you in the next session, we'll make sure that we cover limiting and excess reagents, and then hopefully we'll manage to ramp it all the way up to the top. At this point, I'm not yet planning on doing a masterclass in stoichiometry, but I think if enough of you get decent mastery on it, I may consider adding one in. All right, so please, by all means, if you want to push, if I see enough people really taking it seriously, I will happily put in an impossible question or session for the people that have been working on it. All right. Any last questions before we end?
Ma'am, can you please go through what's this now? Number 2 again of exercise 6. Because I still don't see how you got it.
Okay.
Yeah.
Miller, stay on here and I'll do it in just a second. All right. Okay. Can I ask everybody else, and I know I do this every time we do this, can everybody quickly turn on their cameras so that I can just say hello to all of you and then wave goodbye and then have a lovely evening? And I shall see you all hopefully tomorrow for chemical equilibrium. All right. Bye-bye. Okay. Pleasure. Bye-bye, Josh. All right, so I ended up making a mistake here. What I did right at the end was I forgot that what I was looking for was on the denominator. So therefore, please, correction, that should have been the answer over there. All right, apologies for that.